somewhere in the warm, dark water of the western Atlantic, in a quiet patch of sea no fishing boat ever crowds, a creature begins its life, and no human has ever seen it happen. Before we go any further, if you want a brand new Earth topic every single night to fall asleep to, subscribe. One tap and a new story is waiting for you every evening. The creature is an eel, a simple, slim, ancient animal, and the place it is born is one of the strangest patches of ocean on our planet. Picture, for a moment, the whole Earth from very far away. A soft blue sphere, turning slowly, half lit by the sun. The oceans wrap around it in a single great body of water, dark and salt and quiet. If you let your eyes drift toward the middle of the Atlantic, between the long coast of North America and the bulge of West Africa, you find a wide oval of warm sea. Sailors once called it the Sargasso. It is a sea inside a sea. There is no shore around it. Instead, slow ocean currents form its walls, turning in a vast, lazy circle. On the surface, golden mats of seaweed drift in long ribbons. The water below is a deep, clear blue, almost purple where the light fades. There are no rivers feeding it, no cliffs framing it, just open water in every direction, hushed and still. This, scientists believe, is where the European eel begins. A creature that will, one day, swim thousands of miles to a small stream in France, or Ireland, or Italy, or Morocco. And then, decades later, it will turn around and swim all the way back to this exact patch of sea to spawn and die. No person has ever watched it happen. Not once. Not in all the centuries we have studied the ocean. We have found the tiny, leaf-shaped larvae drifting near the Sargasso. We have tracked adult eels heading east into the deep Atlantic with satellite tags. But the moment of birth, the gathering of the breeders, the eggs themselves, these things have stayed hidden. The eel keeps its first and last secret very well. This is where our long, quiet question begins. How does a finger-thin young eel, born in the middle of an ocean, find its way across thousands of miles to a small river it has never seen? And how, years later, does the same animal, now grown long and silver-eyed, find its way back to a specific stretch of warm water in the open sea? There are no landmarks, no paths, no parents to follow. Only water and current and some inner sense we still do not fully understand. The eel is just one traveler in a much larger story. All across the earth tonight, animals are moving. Tiny songbirds are crossing deserts in the dark. Whales are humming low songs across thousands of miles of ocean. Sea turtles are pushing through black water toward beaches their mothers once knew. Caribou are walking slowly along trails older than any village. Butterflies, the weight of a paperclip, are riding the wind toward forests they have never seen with their own eyes. And in every one of these journeys, the same gentle puzzle hides. We can describe what the animals do. We can map their routes. We can count their numbers and weigh their bodies and follow them by satellite. But the deeper question, how they actually find their way, remains, in many cases, only partly answered. Some researchers suggest they read the Earth's magnetic field like a soft, invisible map. Others wonder if they follow scent trails carried by currents, or memorize the slant of the stars, or feel the angle of polarized sunlight through a thin sky. Most likely, it is some quiet blend of all of these. But the exact recipe is still uncertain. That is the thread that will run through our long, slow night together. Not a single fact, a single open question, examined from many angles, in many places, with many animals. The eel will lead us in. Others will join along the way. We will sit with what is known, and we will sit with what is not known, and we will let both feel equally welcome. So settle in. Let your shoulders soften. Let your breath slow. Imagine the Sargasso Sea, warm and dark and lit only by starlight on its surface. Somewhere below, tonight, an eel begins its long way home. We do not yet know exactly how. And that is the mystery we will keep gentle company with all the way until you fall asleep. Let us begin with the simplest picture, and then slowly let it grow strange. An eel is a long, slim fish. It can be as thin as a finger or as thick as your wrist. It can grow longer than your arm, and in some cases, longer than a tall person is tall. Its body is smooth and muscular, the color of wet stone or old bronze, with a soft, pale belly. It moves through water by rippling, head to tail, ribbon drawn through dark glass. The eel we will sit with tonight is the European eel. It lives, for most of its long life, in fresh water. You can find it in rivers, in slow streams, in muddy ponds, in lakes tucked behind quiet hills. It hides under stones. It rests in the soft brown silt at the bottom. It hunts at night when the world above the water is still. By day, it tucks itself into shadows and waits. A single European eel may live in the same little stretch of river for many years. 20 years, 30. Some are thought to live longer than a human lifetime, in rare cases passing 80 years before they are ready to leave. To picture that, imagine a child who grows up beside a small creek, learns to walk, grows old, and the same eel is still there in the same dark pool, slow and patient under the same mossy stone. Now hold that picture, because here is where the simple story turns into a mystery. Not a single European eel has ever been seen breeding in fresh water. Not one. In all the centuries that people have fished these rivers, cooked these eels, studied these eels, drawn them in old books, no one has ever found eel eggs in a river. No one has ever found newborn eels in a lake. The beginning of the eel is not in the place where the eel lives. Their nursery is somewhere else, somewhere far away, somewhere in the open sea. The best clue we have points to a wide patch of warm, salty water in the western Atlantic Ocean called the Sargasso Sea. It is a strange place. It has no shores. It is a sea defined not by land, but by currents. A slow oval of water held in place by the great spinning of the North Atlantic. The surface is often calm. Golden mats of floating seaweed drift across it in long, lazy ribbons. Below, the water is deep blue and clear and quiet. The Sargasso Sea is enormous. It covers roughly 2 million square miles of ocean. If you laid the entire country of India inside it, there would still be room left over. And yet, somewhere within all that empty blue, every European eel in every river in Europe is thought to be born. Eels from Spain, from Ireland, from Norway, from Italy, from tiny mountain streams in the Alps. All of them, one sea, one vast, hidden cradle. We say thought to be born, because here is the part that is still unsolved. human being has ever seen a European eel lay an egg. No one has ever seen two adult European eels meet in the open ocean. No one has ever found a pair alive in the act of breeding. We have found their smallest babies drifting in the Sargasso water, tiny and clear, shaped like willow leaves. From those babies, we can guess where the parents must have been. But the parents themselves remain unseen. One idea is that the eels gather deep below the surface, perhaps 1,000 feet down, in water that is dark and cool and largely unstudied. Another idea is that they spread out over a wide area and meet only briefly in the night in very small numbers, which would make finding them almost impossible. A third possibility is that we have been looking in slightly the wrong patch of sea, and the true nursery lies a little to the east, or a little deeper, or a little later in the year than our research ships have been able to follow. So this is the basic shape of the mystery before we go any further. A common fish found in nearly every river in Europe lives most of its life in fresh water. To breed, it travels thousands of miles across the open ocean to a sea with no edges. There, in a place we cannot quite pin down, it does something we have never witnessed, and then it disappears. That is what we know. That is also, in a strange and lovely way, almost all we know. The nursery is real. The map to it is not yet drawn. We will sit with that thought gently as the night grows quieter. Long before a young eel ever feels the pull of a river, before it has eyes that can see, or a body shaped like a ribbon, it begins as something almost invisible. A tiny egg drifting in warm water somewhere in the western Atlantic. No one has ever watched this happen in the wild. No one has ever filmed an egg of the European eel in its natural place. We believe it occurs. We have seen the larvae that come after. But the first moment of life remains, even now, a kind of educated guess. The story, as best we can tell, begins in a strange patch of ocean called the Sargasso Sea. It is not a sea with shores. It is a vast oval of slow blue water in the middle of the Atlantic, ringed by ocean currents that turn around it like a quiet wheel. Mats of golden sargassum weed float on the surface, drifting in long, soft lines. Below, the water is unusually clear and deep, a soft indigo that fades into darkness. Somewhere in this enormous, calm place, eels are thought to spawn, and then, almost at once, the long drift home begins. The newborn larva is called a leptosphalus. It is shaped like a thin, see-through leaf, no bigger than a fingernail at first. Light passes right through its body. You could hold one in your hand and barely know it was there. This tiny leaf shape is not strong. It cannot swim against a current. It cannot choose a direction the way a fish might. Instead, it gives itself over to the slow rivers of the ocean. The main river it rides is the Gulf Stream, a wide band of warm water that curls up from the Caribbean, sweeps along the eastern coast of North America, and then bends out across the open Atlantic toward Europe. The journey can take a year. It can take 2 years, or even 3. Estimates vary, and that variation itself is part of the mystery. We do not know exactly how long any single eel drifts. We only know they arrive. Picture that drift for a moment. A leaf-thin creature, smaller than a coin, suspended in blue water that goes down for miles beneath it. The sun above turns the surface into a shifting ceiling of light. Below, the cold dark holds its silence. The little larva feeds on tiny scraps of organic matter floating in the water, growing slowly, almost imperceptibly. Around it, the ocean rolls on. Storms pass overhead. Whales move through the deep. The leaf drifts on. How did this strange way of being born come to exist at all? That is one of the deeper puzzles. One idea is that the eel's ancestors once lived only in the open sea, and that rivers were a later home, added on as the continents moved and new freshwater habitats opened up. In this view, the long return to the Sargasso is a memory of an older life, a kind of ancestral homing, locked into the species long before Europe, and the Americas were shaped as we know them. Another idea is almost the opposite. Some researchers wonder whether the spawning ground drifted with the continents themselves, slowly shifting as the Atlantic Ocean widened over tens of millions of years. In that case, the eels of today are simply following a route that used to be much shorter. Both ideas are reasonable. Both leave gaps. We do not have a clear fossil record of ancient eel breeding grounds. We cannot watch the ocean's currents from 100 million years ago. So the origin of this enormous round trip remains, for now, a story we are still piecing together. What we can say is that the conditions had to be very specific. The Sargasso Sea is unusually warm, unusually salty, and unusually still. It sits inside a slow rotation of currents that helps keep things in place long enough for fragile larvae to begin life. Then, those same currents lift the larvae gently outward and carry them across the ocean. It is as though the geography of the Atlantic itself has been shaped by chance or by deep time into a kind of cradle and conveyor belt. For the drifting leaf, none of this is conscious. It does not know it is heading toward Europe. It does not know the rivers are waiting. It only knows the warmth of the water around it and the slow press of the current behind it. And yet, somehow, the body inside that leaf already carries the plan. The change has not begun. The shape has not yet shifted. But the journey, in its first quiet form, is already underway. To follow a single eel through its life is to watch one body become four. Few animals on Earth change shape so completely. Fewer still do it while drifting through such different worlds. The eel begins as something so small and clear it barely seems alive, and it ends as a silver traveler built for the open sea. Between those two forms lie shapes the early naturalists did not even recognize as the same creature. The first body is called a leptosphalus, which simply means slender head. It is a tiny leaf of living glass, flat and transparent, shaped like a willow leaf, no longer than a fingernail. Light passes straight through it. The blood inside runs almost clear. The bones are soft and pale. If you held one in your palm, you might mistake it for a sliver of jelly carried in from the tide. This is the form in which the young eel drifts for months, perhaps years, riding ocean currents across thousands of miles. Its body is built for floating, not swimming. The flatness gives it lift in the water, the way a paper kite catches air. What this little leaf is made of links it back to deep time. Its flesh is mostly water, and that water may be older than the planet itself. Some researchers wonder whether much of Earth's ocean arrived on icy comets and dust grains long ago, while others argue the water was always here, locked inside the minerals that formed our young world. The question is still open. Either way, every cell in the drifting larva carries traces of that ancient story. The salt in its tissues holds atoms of sodium and chlorine forged in stars that died long before our sun was born. When the leptosphalus nears the coasts of Europe or North Africa, it changes for the first time. It shrinks. Its body narrows and tightens into a thin pencil of clear flesh, no longer leaf-like, but rod-like. This second form is called the glass eel. The name fits. You can see the faint shadow of its spine through its skin. You can count the dark dots of its eyes. Glass eels gather at river mouths in great quiet drifts, waiting for the right tide, the right temperature, the right unknown signal to push them inland. What that signal is exactly remains debated. Some scientists point to changes in salt and scent. Others suspect the moon, or the slow shift of the seasons, or cues we have not yet learned to measure. Inside the river, the eel changes again. Color floods its body. The clear flesh darkens into brown and yellow and olive green. Its skin thickens. Its muscles grow stronger for pushing against fresh current. This third form is called the yellow eel, and it is the shape the eel wears for most of its life. Yellow eels can live for 10 years, 20 years, sometimes far longer, hidden in ponds and ditches and slow stretches of river. They eat, they grow, they wait. And during all those quiet years, something inside them seems to remember the sea. The fourth change is the strangest. One autumn, often after many seasons of stillness, the eel begins to transform without leaving its hiding place. Its belly turns silver. Its back darkens to a deep bronze or black. Its eyes grow larger, swelling to take in the dim blue of the open ocean it has not seen since it was a leaf. Its stomach shrinks and stops working because it will not eat again. Its bones harden. Its fins lengthen. This is the silver eel, and it is built for one final voyage back to the sea where it was born. What triggers this last transformation is still uncertain. One idea is that the eel reaches some inner threshold of size or fat reserves. Another is that subtle changes in day length and water temperature flip a hidden switch. A third possibility is that several signals must arrive together, and that no single cue is enough. The eel itself gives no answer. It only changes, and then it leaves. Each of these four bodies is made from the same building blocks the rest of the living world shares. Carbon from ancient forests and ancient seas, calcium drawn from stone dissolved by rain, iron in tiny traces that was forged inside dying stars and scattered across space long before Earth gathered itself together. The eel rearranges these old materials 4 times in a single life, as if rehearsing some quiet instruction written into its cells. What that instruction is, and how it knows when to act, are questions we have not yet answered. For now, the eel keeps its secret and changes and goes. For most of its life, the eel is a creature of fresh water. It lives in slow rivers, in quiet ponds, in muddy ditches where the light barely reaches. Its body is yellow-brown along the belly, dark along the back. For 10 years, 20 years, sometimes 50, it lives this hidden life. It hunts at night. It hides under stones by day. It seems, by every measure, to belong to the land it has chosen. Then one autumn, something inside the eel begins to change. We do not know exactly what triggers it. We have ideas, but the trigger itself remains hidden inside the eel's own quiet body. Perhaps it is age. Perhaps it is a slow building of fat reserves. Perhaps it is some inner clock counting down through the years. Whatever the signal is, the eel begins to transform. Its belly turns a bright, polished silver. Its back darkens to a deep gunmetal blue. Its eyes grow larger, sometimes doubling in size, and the cells inside them shift to see in the blue light of the deep sea, a place this eel has never been. Its stomach begins to shrink and dissolve. It will never eat again. Its skin thickens. Its fins grow longer. Its whole body is being rebuilt in secret for a single voyage. This is the silver hour. The river eel becomes the silver eel. And on a certain night, often during a new moon when the sky is darkest and the rain is falling, the silver eel slips downstream toward the sea. What pulls it out of the fresh water? This is one of the quieter mysteries. The moon seems to matter. Many of the great downstream runs happen on the darkest nights, when there is no moonlight on the water. Some researchers think the eels prefer the cover of darkness to avoid being seen by predators. Others wonder if the eels are reading the moon itself, using its absence as a kind of timing cue, a signal that the tides and currents are aligned for the long journey ahead. Rainfall seems to matter too. A swollen river full of fresh runoff gives the eels a downhill push and a strong scent trail to follow. But none of these forces on their own fully explain the timing. The eels seem to wait, and then they seem to know. Once they reach the sea, they face a world ruled by forces they have never encountered. There is salt now where there was none. There is pressure that grows heavier with every meter of depth. There are currents that move like enormous rivers within the ocean, some warm, some cold, some flowing east, some flowing west. And there is the Earth's magnetic field, a vast, invisible web of lines that wraps the whole planet from pole to pole. The silver eel seems to use all of these. Tagging studies have shown that the eels often swim deep by day and shallower by night, riding a slow rolling pattern up and down through the water. One theory is that they are using temperature layers to conserve energy, slipping into warmer water when it helps, and into colder water when it shelters them from predators. Another theory is that they are tasting the chemistry of different water masses, following invisible scent corridors across thousands of kilometers. A third idea is that they are reading the magnetic field itself, using it like a chart, with the strength and angle of the field telling them roughly where on Earth they are. The truth may be some weaving of all three. The truth may be something else entirely. We do know that they are not random in their wandering. The silver eels of Europe seem to head, more or less, in the right general direction. They are pointed toward the Sargasso Sea, that quiet patch of warm water far out in the Atlantic. Even though no eel in the group has ever been there before, their parents made the journey, spawned, and died. Their map, if it is a map, was never taught to them. It must have been built into the body itself, written somewhere in the cells, waiting for the silver hour to arrive. How a soft, slender fish with no eyes that have ever seen the open ocean manages to set a course across half a sea, guided by forces too faint for us to feel, is something we still cannot fully answer. We can describe the pieces. We can measure the currents. We can map the magnetic field. We can watch the moon and the rain. But the eel, sliding out of its quiet river on a dark, wet night, seems to know something we have not yet learned to read. Tonight we turn from the eel to another famous wanderer of water, the salmon, a fish that begins its life in a small stream, sometimes no wider than a country road, and ends its life in that same small stream after years at sea. To feel the size of this mystery, it helps to picture the distances involved. So let us slow down and stretch them out in the mind. Imagine a single gravel bed in a forest. The water there is shallow and cold. You could step across it in 2 strides. The pebbles are the size of marbles, and between them, a young salmon hatches. It is no longer than your little finger. For weeks, it knows only the smell of that water, the taste of those rocks, the shadow of those trees. Then it leaves. It drifts downstream, growing as it goes. It passes from creek to river, from river to estuary, from estuary to the open sea. By the time it reaches salt water, it has already traveled farther than most people walk in a year. And the sea has barely begun. A Pacific salmon may swim out into the open ocean for thousands of miles. Some travel from rivers in Idaho all the way to the waters near Japan and back. That is a round trip of more than 6,000 miles. To picture it, think of a single fish, no longer than your forearm, crossing a stretch of water so wide that a passenger jet would need 10 hours to fly over it. And the salmon does this without a map, without a coastline to follow, without ever rising above the waves to see the stars clearly. Try to feel the scale another way. If the salmon's home stream were the size of a coin on your kitchen table, the ocean it must cross would stretch out past the walls of your house, past the end of your street, past the edge of your town, and somewhere out there, after years of feeding and growing, the fish would turn around. It would come back, and it would land on that exact coin, This is what makes the salmon's story sit so strangely in the mind. The journey is enormous. The target is tiny. The error allowed is almost none. A salmon does not just return to the right river. It returns, in most cases, to the very same bend of the very same tributary where it hatched. A patch of gravel the size of a parking space, found at the end of a journey longer than the width of a continent. How does it do this? The honest answer is that we have pieces, but not the whole picture. One leading idea is that salmon use the Earth's magnetic field as a kind of broad compass during their years at sea. Studies of young salmon in tanks suggest they can sense the angle and strength of magnetic lines, which vary across the globe like an invisible grid. This would give them a rough sense of where they are within the ocean basin. A competing and complementary idea is that smell does the final work. As the salmon nears the coast, it seems to recognize the chemical signature of its home river. Each stream carries a unique blend of minerals, plants, soils, and bacteria. The fish may have memorized this scent as a fingerling, locking it into memory during a short window of early life. Yet researchers still argue about how much of the journey is magnetic, how much is chemical, and how the two senses hand off to each other along the way. To grasp the difficulty, picture trying to find one specific house in one specific town on one specific continent, while blindfolded by smell alone after walking for 4 years. Now do it underwater. Now do it without ever having seen a map. The salmon does something close to this again and again, generation after generation. With a brain smaller than an acorn, the scale becomes even stranger when you remember how brief the homecoming is. After all those miles, the returning salmon may live only days or weeks in the home stream. It spawns, it rests, it dies. Its body feeds the forest. Bears, eagles, and even the roots of old trees draw nutrients from salmon that were born in that same water and somehow found their way back. We can measure the distances. We can track the temperatures, the currents, the magnetic readings. We can sample the scent of a stream down to the last trace mineral. And still, the moment of recognition, the instant the salmon knows it is home, remains hidden from us. Somewhere inside that small body lies a memory we have not yet learned to read. And tonight, while you drift, that quiet memory is still working out there, in cold water, in the dark. Picture for a moment the open Pacific just before dawn. The water is dark, slate blue, almost black at the edges, and it lifts in long, slow swells that travel for thousands of miles before they meet any shore. There is no land in sight. There are no birds yet. There is only the soft hiss of wind across the tops of the waves, and the faint pale line of light beginning to gather at the eastern rim of the world. If you were floating here, far from any coast, you might believe you were the only living thing for 100 miles in every direction. And you would be wrong. Below you, a humpback whale is moving. She is 40 feet long. Her body is dark above and pale below. Her skin marked with the soft white scars of a lifetime at sea. Tiny barnacles cling in clusters near her chin and the leading edges of her great flippers. She is heading north, toward feeding waters she has not seen in months, and she is traveling in near silence. This is part of what makes whale migration so strange and so beautiful to think about. Humpbacks and gray whales and blue whales cross entire oceans every year. Some travel more than 10,000 miles between their winter breeding grounds and their summer feeding grounds. They do this without maps, without coastlines to follow for most of the trip, and often without the company of other whales for long stretches at a time. From the surface, you would see almost nothing. A dark back rising, a puff of warm breath catching the early light, a broad tail lifting, glistening, sliding under. Then nothing again for many minutes. If you could float above the root from high enough, you would see only the patterned skin of the sea, long parallel ridges of swell, scattered patches of foam where the wind has torn the wave tops, the deep blue of warm tropical water giving way, mile by mile, to the colder steel gray of higher latitudes. Currents braid through it all in patterns you cannot quite see from up close, but which the satellites show as great slow rivers within the ocean itself. The whale moves through this surface world like a shadow beneath a curtain. How does she know where to go? This is the open question. One idea is that whales hold a kind of mental map built from the magnetic field of the Earth, the same field that turns a compass needle. Some studies have found that whales which strand themselves on beaches seem to do so more often during solar storms, when that magnetic field grows noisy and unreliable. That is suggestive, but it is not proof. Other researchers wonder whether whales read the long, low-pressure waves that travel through deep water, or follow the position of the sun across the sky, or remember the taste and temperature of certain currents from earlier crossings. There is a competing view that says no single sense explains it. The whale, in this view, layers many faint clues together. The way a person walking home in the fog might use the sound of traffic, the slope of the ground, and the smell of a bakery all at once. Take any one cue away, and she still arrives. Take several away, and she may drift. Which of these ideas is closer to the truth? We do not yet know. What makes the silence so curious is that whales are famous for their songs. Humpback males sing long, looping melodies in their breeding waters that can carry for many miles through the deep. Blue whales produce some of the lowest sounds any animal makes. Deep pulses that, in the right conditions, can travel across entire ocean basins. Yet, during the long migration itself, many whales seem to go quiet. They cross thousands of miles without singing. Some researchers think they may still be listening, picking up faint, distant calls from other whales, or the low rumble of distant coasts. Others suspect the silence is simply rest, a saving of energy for the journey ahead. The question is open. So if you stood on the deck of a small boat at dawn, somewhere far out where the chart shows only blue, you might watch the sea for a long time and see nothing. And then, very close, a slow gray back would rise without warning. A breath like a soft sigh. A glimpse of an eye, calm and ancient, glancing once at the surface world. Then she would be gone again, sliding down into water you cannot read, following signs you cannot sense. On her way to a place she has somehow always known how to find. Beneath the warm shallows of a tropical beach, a sea turtle hatchling pushes its way up through the sand. It is no larger than the palm of a hand, soft-shelled, dark-eyed, blinking at a world it has never seen. The moon hangs low over the water, and the little turtle scrambles toward the brightest horizon. Within minutes, it is in the surf, paddling away from the only patch of earth it will know for decades. And yet, somewhere inside that tiny body, a quiet map is already forming. Sea turtles are among the great wanderers of the ocean. They drift across whole basins, riding currents for years, feeding in waters thousands of miles from the beach where they were born. Then, when the time comes to lay their own eggs, the females return, not just to the same coastline, often to the very same stretch of sand. The mystery sits inside that simple act. How does an animal, after 20 or 30 years at sea, find one small beach again? One leading idea is that sea turtles carry a kind of soft compass inside them. They seem to sense the Earth's magnetic field, the invisible web of force that wraps the whole planet. The field is not the same everywhere. It tilts and strengthens in patterns, and every coastline has its own quiet magnetic signature. Researchers think a hatchling may learn the signature of its birth beach during those first moments in the surf, and then carry that memory like a faint song for the rest of its life. The evidence is gentle but real. In careful experiments, hatchlings placed in tanks ringed with magnetic coils have changed their swimming direction when the field around them is altered. Adult females tend to nest on beaches whose magnetic signatures match the ones they left as hatchlings. When the field of a coastline shifts a little over the decades, the nesting pattern seems to shift with it, like a needle following a slow drift. Still, no one has found the organ that does the sensing. There is no clear magnetic compass inside a turtle's head that scientists can point to and say, "This is where the map lives." Some researchers wonder whether tiny crystals of a mineral called magnetite, found in many living tissues, act as little needles inside certain cells. Others think the answer may lie in special proteins in the eye, proteins that react to magnetic fields in ways we are only beginning to understand. Both ideas have support. Neither has been confirmed. There may be more than one sense at work. Sea turtles also seem to use the angle of sunlight, the slow swell of long ocean waves, and possibly the chemistry of the water itself, the deep ocean carries faint smells, drifting plumes of minerals and decay and life. And a turtle's nose is more sensitive than its calm face suggests. Some scientists think the magnetic sense gets a turtle close, within tens of miles of its home coast, and then smell and memory carry it the rest of the way. Others think the magnetic map alone is precise enough. The question stays open. What makes the mystery deeper is the time involved. A loggerhead may spend its first decade drifting in the open Atlantic, carried by the great spinning current that loops between the Americas, Europe, and Africa. During those years, it grows from the size of a coin to the size of a dinner plate. It feeds, hides, sleeps among floating mats of seaweed. And through all of it, somehow, the soft compass inside it keeps a connection to a single dark beach it has not touched since the night it was born. We cannot yet record what a turtle senses as it swims. We can place small transmitters on their shells and watch the lines of their travel appear on a map. We can see the long, graceful arcs across oceans, the strange pauses, the sudden turns toward home. But the inner picture, the felt sense of where the world is pulling, remains hidden from us. It is as if we are reading the outside of a long letter without ever opening it. There is something tender about that thought. A creature older than most forests carries inside it a sense we do not have, pointing toward a beach we cannot feel. It moves through dark water with quiet certainty, guided by something soft and old, while we float above in our boats and wonder. For tonight, let the picture settle. A small turtle, decades grown, gliding through warm water at night. The stars dim above the waves, the shore not yet in sight, and deep within her, a faint, patient pull, leading her toward a strip of sand she has carried in memory for half her life. There is a bird called the common swift that may go almost a year without ever touching the ground. It eats in the air. It drinks from raindrops in the air. It mates in the air. And, as best as anyone can tell, it sleeps in the air too. Once a young swift leaves the nest where it hatched, it may not land again for 2 or 3 years. It simply flies through days, through nights, through storms, through quiet evenings of pink light. Think about that for a moment as you rest. While you lie warm in your bed, Somewhere above the slow turning of the world, there are small dark shapes still moving through the sky. Their wings curve like tiny crescent moons. They cut soft arcs through the air, hour after hour, with no place to set their feet. The mystery of how they manage this is one of the gentler puzzles of bird migration. We know from tiny tracking devices that swifts spend 10 months of the year aloft. We know they climb high into the cool layers of the evening sky, sometimes 2 miles up, and circle slowly there through the dark hours. We know their hearts keep beating, their wings keep working. But how they truly sleep up there, no one can say for certain. One theory is that swifts use a trick found in some other birds. The trick has a long name, but the idea is simple. Half of the brain rests while the other half stays awake. One eye closes, the other watches. Then they switch. Ducks do this when they sleep on open water. Dolphins do it under the waves. It may be that swifts do something similar, slipping into half sleep as they glide on rising columns of warm air. A different idea is that swifts take very short naps, seconds long, quick little dips into rest, scattered through the long night, while their wings carry them on the wind by sheer practice. No one has yet caught a swift in the act of sleeping in the wild. The sky is too wide. The bird is too small. The truth is still drifting somewhere above us. This is the rhythm we are sitting with tonight. The cycle of waking and resting that all living things must follow, but bent into strange new shapes by the demands of migration. For most creatures, sleep means stillness. A burrow, a branch, a quiet hollow under leaves. For the swift, sleep means motion. The body keeps moving even when the mind softens. Other migrating birds bend the rhythm in their own ways. The bar-tailed godwit, a long-legged shorebird with a slender curved beak, flies from Alaska to New Zealand without stopping. 8 or 9 days in the air. No food, no water, no landing. Some have been tracked covering more than 7,000 miles in a single unbroken flight. Whether they sleep at all during this crossing, or simply push through on something deeper than sleep, is still being studied. Songbirds have their own cycle. Many of them migrate at night when the air is cooler and predators are fewer. During the day, they rest and eat. During the migration season, their bodies seem to switch into a different kind of sleep. Short bursts, quick recoveries, a rhythm that lets them fly for hours under the stars, and then doze in brief flickers when dawn comes. What is striking is how the cycle of the earth itself seems to set the tempo. The turning of day into night, the slow tilt of the planet that brings the seasons, the pulling of light across the hemispheres as summer drifts from north to south and back again. Birds read these signals deep in their bodies. Hormones rise and fall. Restlessness builds. Then, on some quiet evening, the urge to go becomes too strong to resist. We still do not fully understand what tells them when to begin. Day length plays a role. Temperature plays a role. The angle of the sun, the pull of the magnetic field, the taste of the wind. All of these may matter, woven together in a way no single instrument can measure. The bird knows. The bird simply lifts into the air and goes. And the swift, perhaps, knows the most ancient version of this rhythm. The swift was shaped by the sky itself. Its tiny feet are almost useless on the ground. Its long curved wings are made only for air. To rest, it must rise. To sleep, it must keep flying. Its whole life is a slow circling of the planet, broken only by the brief weeks of nesting. We may never know exactly how that small dark shape closes its eyes above the clouds. For tonight, we can simply imagine it. Quiet wings, quiet breath, the world turning below. Among all the wandering creatures of the earth, the monarch butterfly may be the strangest traveler of all. The eel disappears into the sea. The salmon climbs a river it once knew as a fry. But the monarch flies toward a forest it has never seen, has never been told about, and could not possibly remember. And yet, somehow, year after year, it finds the same patch of trees on the same slopes of the same quiet mountains in central Mexico. The journey is long and slow and beautiful. In late summer, across the wide fields and gardens of eastern North America, a special generation of monarchs is born. They are not like their parents. They will not mate right away. They will not flutter from flower to flower for only a few short weeks. This generation is built for one purpose, and purpose is the long flight south. Some call them the Methuselah generation because they live many times longer than the butterflies that came before them. Their bodies are slightly larger. Their wings are slightly stronger. Something inside them has shifted quietly in response to shorter days and cooler nights, and then they begin to drift on paper-thin wings, riding warm air currents toward a destination they have never visited. The astonishing part is this: the monarch that started the trip is not the monarch that ended last year's trip. Several generations have passed in between. The butterflies leaving Canada in autumn are the great-great-grandchildren of the butterflies that left those same Mexican mountains the previous spring. No single butterfly makes the full round journey. The memory, if you can call it memory, lives somewhere in the species itself, not in any single small creature. How does a butterfly born in a meadow in Ontario know to fly toward a forest in Michoacan it has never seen? This is one of the gentlest and most stubborn mysteries in all of animal migration. Researchers have studied the monarch with quiet patience for decades. They have found that the butterflies use the position of the sun as a kind of compass, but the sun moves across the sky throughout the day. So a sun compass alone would send the butterflies in circles. The monarchs solve this by keeping track of the time of day with a tiny internal clock tucked away in their antennae. They combine the angle of the sun with the hour to find a steady direction. Remove the antennae or shift the clock, and the butterfly loses its way. But the sun compass is only part of the puzzle. On cloudy days, monarchs still fly south. Some studies suggest they can also sense the Earth's magnetic field, using tiny particles in their bodies that respond to magnetism. One theory holds that the magnetic sense and the sun compass work together, each correcting the other. A competing theory suggests that the magnetic sense is only a backup, used when the sky is hidden. Both ideas have evidence on their side. Neither has won out. And even if we accept that the butterfly knows which way is south, that does not explain how it knows when to stop. The overwintering forests in central Mexico are small, scattered patches of oyamel fir trees on cool, misty mountain slopes. The butterflies arrive in vast numbers, sometimes hundreds of millions, and cluster on the same trees their ancestors once clung to. Some researchers wonder if there are landmarks the monarchs read from the air, the shape of distant ridges, or the smell of fir resin drifting on cold mountain wind. Others wonder if temperature itself acts as a final cue, a gentle threshold that tells the butterfly it has arrived. The honest answer is that we are still guessing. There is something tender about all of this, a creature lighter than a coin, with a brain smaller than a grain of rice, completes a flight of 3,000 miles to a forest it has never seen. Guided by signals we are only beginning to understand, and the neighbors of the monarch, the milkweed that feeds its caterpillars, the wildflowers that fuel its long flight, the fir trees that shelter it through winter, the cool mountain mists that keep its wings still. All of them are part of the puzzle. Pull one thread, and the whole of the journey trembles. The monarch reminds us that migration is never the work of one animal alone. It is a slow conversation between a creature and a continent, between a small body and a wide, patient earth. We listen in on that conversation as best we can, with our nets and our tags and our careful counts. But the deepest part of the monarch's knowing still rests, soft and folded, somewhere we cannot yet reach. Far in the north, where the trees thin out and the ground stays frozen just below the surface, the caribou walk. They have been walking these paths for a very long time. Some of the trails worn into the tundra are thousands of years old. Hooves have pressed the same soft lines into the same valleys, generation after generation, since the last ice age began to loosen its grip on the land. The caribou is built for this. Its hooves spread wide on snow and pull tight on rocky ground. Its coat is hollow, each hair a tiny tube of trapped air, holding warmth against winds that can freeze skin in minutes. Its nose is a quiet wonder of plumbing, warming each breath before it reaches the lungs. Everything about the animal is shaped for the long walk, and the walk is long. Some herds cover more than 3,000 miles in a single year. That is farther than any other land mammal travels on Earth. They move between summer, calving grounds near the coast and winter feeding grounds deep in the boreal forest. Then back again. The great loop drawn across the top of the world. The porcupine herd, named for the river it crosses, makes one of the longest of these migrations, moving in slow rivers of animals across Alaska and the Yukon. The herds themselves can be enormous. In good years, hundreds of thousands of caribou move together, the tundra rippling with their bodies. From a low ridge, they can look like a single living thing, brown and gray and white, breathing out clouds of mist into the cold air. The ground softens beneath them. The lichen they feed on is crushed and scattered, then begins to grow back over the years that follow, waiting for the herd to return. How they know where to go remains an open question. The trails are ancient, yes, but the animals walking them today have never seen the full route before. A young caribou follows its mother, and its mother followed hers, and the memory of the path seems to pass down through the herd as much as through any single mind. Some researchers think the lead animals, often older females, carry a kind of learned map, refined by decades of walking. Others wonder whether the caribou also read cues in the land itself. The shape of a ridge, the smell of a certain river, the angle of the low sun on the snow. There may be more. Caribou, like many migrating animals, seem to sense the Earth's magnetic field. Studies of resting and feeding herds suggest the animals often align their bodies along a north-south line, even when wind and sun would suggest otherwise. Whether they use this sense for long-distance navigation or only for small daily orientation, no one yet knows. The question sits with the herd as it moves. The extremes of their world are hard to picture from a warm room. In midwinter, the sun barely rises. Temperatures fall to 40, 50, 60 degrees below zero. The caribou dig through the snow with their hooves to reach the pale green lichen beneath, a plant that grows so slowly. A single patch may be older than the oldest trees in the forest. In summer, the same animals stand in clouds of mosquitoes, thick enough to drain blood from a calf. They climb to windy ridges and patches of late snow, just to find a little relief. Through all of it, the trails hold. Satellite tracking has shown that herds will often choose the same river crossings their ancestors used, even when easier crossings exist nearby. The knowledge of where the ice is thin, where the current is gentle, where the far bank rises in a soft slope. That knowledge seems to travel with the herd across the centuries. When a crossing is lost, blocked by a new road or a flooded valley, the herd sometimes circles for days, searching for a memory the land no longer matches. Some of the oldest human paths in the north were first caribou paths. People followed the herds, and the herds followed the old routes, and together they wore lines into the tundra that are still visible from the air. To stand on such a trail is to stand on something older than any city, any written language, any story still being told around a fire. And yet, the deepest question remains: how does a young caribou, born in spring on a windy coastal plain, come to know the way south through 1,000 miles of forest it has never seen? What does it feel in its body that tells it the time has come to walk? The herd moves on, quiet and steady, carrying its answer with it. In a quiet stretch of sea off the eastern coast of Central America, something strange happens each year. Hundreds of scalloped hammerhead sharks rise from the deep water and gather around the slopes of an underwater mountain. They drift together in slow, silver formations, their wide heads turning gently in the current. For a few weeks, they circle, they mingle, they seem to wait. And then, without warning, they scatter back into the open ocean, vanishing in directions no one can fully trace. These gatherings have been watched by divers for decades, and they remain one of the softest puzzles in the study of animal movement. The sharks do not appear to feed during these meetings. They do not appear to breed there either. They simply assemble, sometimes by the hundreds, around the same underwater peaks year after year. Then, by some shared cue no one has recorded, they leave. One theory is that the sharks use these seamounts, tall, lonely mountains rising from the deep seafloor, as a kind of resting place between long journeys. The water around a seamount often swirls in slow eddies, and prey gathers in those swirls. A hammerhead could pause there, recover its strength, and then push on. Another idea is that the gatherings are social, that the sharks somehow know one another and meet to exchange information we cannot yet read. A third possibility is that the seamounts themselves are signposts. The iron-rich rocks of these underwater peaks bend the Earth's magnetic field in subtle ways, creating a kind of soft beacon a shark with a magnetic sense might feel. Which of these theories is right, or whether all of them are partly right, remains an open question. The hammerhead's body holds another small wonder. Across the underside of its wide, flat head are tiny pores, hundreds of them, each filled with a clear jelly. These pores are called the ampullae of Lorenzini, and they can detect faint electric fields in the water. A swimming fish gives off a small electric pulse from its beating heart and moving muscles. The hammerhead can sense that pulse from a short distance away, even when the prey is hidden under sand. Some researchers wonder if these same pores might also help the shark feel the slow electric whisper of the Earth's magnetic field as it moves through ocean currents. If that is true, the hammerhead may carry a kind of soft compass in its very skin, but the connection is not yet proven, and other scientists think the magnetic sense lies somewhere else in the body, perhaps in tiny crystals of iron tucked inside the nose. There is another quiet detail in the hammerhead's life. Younger sharks tend to gather in the middle of the school, while older, larger females push toward the edges. The pattern shifts gently as the day moves on. No one knows exactly why. Some think the smaller sharks shelter in the center for safety. Others wonder if the arrangement has to do with mating choices or with the way water flows around the school. The sharks themselves give no easy answer. Other shark species hold similar small mysteries. Whale sharks, the giant spotted ones that drift through warm seas, gather each year off certain coasts when tiny fish release their eggs into the water. The sharks arrive in great numbers, feed quietly, and then leave. Satellite tags show some of them traveling thousands of miles afterward, crossing entire ocean basins. Where they go between gatherings and how they know when and where to return is still being pieced together. Basking sharks, the second largest fish in the sea, vanish from northern waters every winter. For a long time, people thought they hibernated on the seafloor. Now, we know they swim south into deep tropical water, sometimes diving to surprising depths. Why they take these long, hidden journeys, no one fully understands. Each of these gatherings shares the same quiet shape. Many animals arrive at one small place from many far places. They stay for a little while. They leave by paths we cannot follow. The cues that draw them in seem to be invisible to us. Perhaps a shift in the magnetic field. Perhaps a chemical trace carried on a current. Perhaps a memory passed along in ways we do not yet recognize. It is a soft and strange thing to picture. A flat seamount rising in the dim blue water. The slow shimmer of hundreds of silver bodies turning in unison. A current sliding past the rock, and above it all, the open sea, full of cues we have not learned to listen for. The sharks gather. The sharks disappear. And the mystery of how they know to do either remains gently, patiently unsolved. For most of human history, the migration of birds was a quiet puzzle that arrived each spring and left each autumn without explanation. People watched the swallows return to the same eaves. They watched the geese cross the moon in long, ragged lines. And then the birds were gone again, and no one truly knew where. The ancient Greeks wondered if some birds buried themselves in mud for the winter. Others thought small songbirds slept inside hollow trees, or even flew to the moon. These ideas sound strange now, but they came from honest watching. The birds simply vanished, and no one had a way to follow them. The first real clues came slowly, through the patient work of bird banders in the late 1800s. A Danish schoolteacher named Hans Mortensen began placing small aluminum rings on the legs of starlings and storks. Each ring carried a tiny address. When a banded bird was found far away, the finder could write back. Bit by bit, lines began to form across the maps of Europe and Africa. The birds were not sleeping in mud. They were crossing seas and deserts. They were traveling farther than anyone had dared to guess. Still, the deepest question stayed open. How did such small creatures, with brains the size of a pea, find their way across thousands of miles of unfamiliar land? The answer began to surface in the 1950s in a quiet laboratory in Germany. young ornithologist named Gustav Kramer kept European starlings in circular cages during the migration season. He noticed that the birds, even when caged, fluttered and hopped in one particular direction. They were trying to fly the way they would have flown if they were free. Kramer realized he had found a tool. The restless birds were pointing at their invisible map. Kramer began to play with the light in the cage. He set up mirrors that bent the sunlight, so the sun appeared to come from a different angle. The birds shifted their hopping to match the false sun. They were using the sky itself as a compass. This was a quiet revolution. A small bird with no instruments was reading the position of the sun across the hours of the day and adjusting for its slow movement. No one had proven such a thing before, but the sun only explained daytime travel. Many songbirds migrate at night when the sky is dark and the sun is gone. The next chapter belonged to a German student named Franz Sauer, and later to an American researcher named Stephen Emlen. They wondered if night migrants might be reading the stars. To test this, Emlen built a clever device that became known as the funnel cage. It was a small paper funnel with an ink pad at the bottom and a wide opening at the top, covered in fine mesh. A bird placed inside would hop and flutter, leaving tiny inky footprints on the sloped paper walls. The marks showed which direction the bird wanted to fly. Emlen took his funnel cages into a planetarium. He projected the night sky onto the dome above the birds. When the stars were shown in their normal pattern, the indigo buntings inside hopped north in spring and south in autumn. When he slowly rotated the projected sky, the birds rotated their hopping with it. When he removed certain stars from the dome, the birds grew confused. They were reading the constellations. More than that, they were reading the slow turning of the night sky around the pole star, the one fixed point that the other stars circle through the night. The discovery was gentle but enormous. These tiny creatures, weighing less than a handful of coins, were astronomers of a kind. They had learned the geometry of the heavens not from books, but from something written into their young brains during their first weeks of life. Emlen showed that buntings raised without ever seeing a real sky could not navigate navigate it all. The learning had to happen. And yet, even now, questions remain. The sun and the stars explain part of the journey, but birds also fly through thick clouds, through fog, through long stretches where the sky offers no clue at all. Something else must be helping them. Some other sense, quieter and harder to find. Each generation of researchers has carried Emlen's funnel forward a little further, and each generation has been left with a wider question than the one before. The map inside the bird is real. We have seen its edges. We have not yet seen its center. There is a sense that many animals seem to carry inside their bodies, and we still cannot fully explain how it works. It lets them feel the earth itself, the slow, invisible field that wraps the whole planet like a soft blanket of force. We call this sense magnetoception. The name sounds tidy. The reality is one of the strangest puzzles in biology. The Earth's magnetic field is a quiet thing. It hums out from the molten iron deep in the core, curving through the rocks and the oceans and the air. It is far too weak for a human to feel without machines. And yet, a tiny robin, weighing less than a slice of bread, can read it. A loggerhead turtle, fresh from the sand, can read it. A salmon, an eel, a honeybee, a sea slug, a fox sleeping in a snowy field. All of them seem to know which way the field is pointing. The strange part is that we have found at least two completely different ways this might be happening, and neither one is fully proven. They may both be true. They may both be wrong in the details. The question stays open. One idea sits inside the eye. Some birds appear to use a special protein called cryptochrome, tucked into the cells of their retinas. When a particle of blue light strikes this protein, it can knock a pair of electrons into a kind of trembling dance. The way they tremble depends on the angle of the magnetic field around them. In theory, this means a bird might literally see the field as a pattern of light or shadow laid across its vision. A pale smudge in one direction, a clearer view in another. Imagine looking out at the morning sky and seeing a soft compass painted across it, fading and brightening as you turn your head. That idea sounds gentle, even beautiful, but it lives inside the world of quantum physics, where particles behave in ways that should not survive inside a warm, wet, living body. Most quantum effects collapse in less than a heartbeat when they meet the noise of biology. Somehow, in the eyes of a songbird, they may last long enough to matter. No one is sure why. Some researchers think the protein is shaped in a very particular way that shelters the dance. Others wonder if we are missing something deeper. The second idea is more old-fashioned. It involves tiny crystals of a mineral called magnetite, the same iron-rich stone that makes a lodestone tug at a nail. These crystals have been found in the beaks of pigeons, the noses of trout, the bodies of bees. They are small enough to act like microscopic compass needles, twisting gently as the animal turns. Nerves nearby might feel the tug and send the signal to the brain. This sounds simpler. The trouble is that researchers have struggled to pin down exactly which cells carry the magnetite and exactly how those cells talk to the brain. Some early studies pointed to certain cells in pigeon beaks. Then later work suggested those cells were actually a different kind of cell entirely, part of the immune system. The hunt continues. The little compass needles seem to be there. We just do not yet know who is reading them. Stranger still, some animals seem to sense not just the direction of the field, but its strength and its angle of dip toward the ground. The field tilts more steeply as you move toward the poles and lies flatter near the equator. A sea turtle hatchling slipping into the surf for the first time may be able to feel the dip and the strength together and read them like a pair of numbers, a kind of magnetic map. With those two readings, the turtle knows roughly where on the planet it is. Even in the middle of an empty ocean it has never seen. That a creature the size of a teacup, with a brain the size of a pea, can do this is one of the quiet wonders of the living world. We build satellites and spinning gyroscopes and atomic clocks to do less. And so the mystery sits there, patient and unanswered. Two competing theories, perhaps both at work, perhaps neither complete. A sense that fills the air around us, felt by countless animals every night while we sleep, invisible to our own bodies. The earth speaks in a soft, magnetic voice, and most of its listeners do not have ears. They have something else, something we have not yet named clearly. Somewhere out there tonight, a small bird turns its head against the dark sky and reads a message we cannot see. Far below the surface of every ocean, in the cold dark where sunlight never reaches, something extraordinary happens each evening. As the sky above turns from blue to black, billions of small creatures begin to rise. Tiny fish, shrimp, squid, jellies, and other soft drifting bodies all move upward together. They climb hundreds of meters through the water, feeding near the surface in the safety of darkness. Before dawn, they sink back down into the deep. This is the largest animal movement on Earth, and it happens every single night. Scientists call it the diel vertical migration. The word diel simply means daily. Each evening, this great quiet climb begins all around the planet, in every ocean, in every sea. The total mass of moving life is so vast that early sonar operators thought they had found a false seafloor. They saw a thick layer on their screens that rose at sunset and fell at sunrise. It took years to understand that the layer was alive. It was made of countless small bodies, rising and falling with the turning of the world. The connection to migration is closer than it first appears. Eels, salmon, tuna, whales, sharks, and seabirds all feed on the creatures of this nightly climb, or on the animals that feed on them. The deep sea pulses like a slow heart, and the long journeys of the great travelers ride on that pulse. When a whale dives at dusk to hunt, it is meeting the rising layer halfway. When an eel begins its long drift toward the Sargasso, it passes through these living clouds. The deep migrations and the long migrations are woven together. Many of the climbing creatures carry their own light. They glow with cool blue, and green flickers from chemicals inside their bodies. Some flash to confuse hunters. Some shine soft lanterns under their eyes. Some leave glowing clouds behind them as they swim. The deep ocean at night is not truly black. It is sprinkled with tiny living stars. How exactly so many different species learned to make light, and why so many use it during the nightly climb, remains an open question. One idea is that light helps them find each other in the vast dark. Another idea is that light helps them hide. By matching the faint glow from the surface so hunters below cannot see their shadow. Both ideas may be true at once. The sun shapes this whole pattern in ways we are still measuring. The angle of sunlight, the brightness of the moon, even the slow turning of the seasons all change how high the animals rise and how long they stay. On cloudy nights, the layer climbs higher. On full moon nights, it stays a little deeper, perhaps to avoid being seen. Some researchers wonder if certain animals can sense the polarized light of dusk, the way some birds seem to. Others think the cue is simply the fading of brightness itself. The details are not yet settled. This nightly climb also helps shape the climate. As the small creatures rise to feed, they carry carbon from the surface back down into the deep when they descend. Their waste, their bodies, their breath all become part of a slow, steady fall of material into the abyss. This is sometimes called the biological pump. It moves carbon out of the air, through the surface water, down into the long, cold dark where it can stay for centuries. The earth breathes through this nightly motion. The atmosphere above and the seafloor below are linked by trillions of small climbing bodies. The great migrators feel all of this without knowing it. A salmon hunting at sea finds its prey because the prey is rising toward it. A seabird diving at twilight catches a squid that came up from the cold below. A whale singing across an ocean basin lives in a world shaped by the daily breathing of the deep. The long journeys we marvel at are not separate from the small ones. They are the same system seen at different scales. What we still cannot fully picture is how the climbing creatures themselves coordinate. Many begin to rise at almost the same moment across huge stretches of water. They do not seem to follow a leader. They may each sense the changing light on their own. They may also send signals to each other that we have not yet detected. The ocean each night becomes a quiet orchestra of rising and falling lives, tuned to the sun above and the dark below. And the long travelers, the eels and whales and turtles, swim through this music, carried by a rhythm older than any map. Across the wide plains of East Africa, a great gray river moves over the land. It is not water. It is more than 1 million wildebeest, joined by zebras and gazelles, walking in a slow loop that traces the same vast circle year after year. They cross the Serengeti and the Masai Mara, the rivers and the open grass, following something the human eye cannot see. They are chasing rain. They are chasing the green flush of new grass that rises after a distant storm. And how they know where that rain has fallen, sometimes hundreds of kilometers away, remains one of the gentler mysteries of the moving earth. The wildebeest is a long-faced, shaggy-shouldered animal, gray-brown with a dark beard, born to walk. A newborn calf can stand within minutes and run within hours. It has to. The herd does not wait. The great loop begins each year in the southern Serengeti, where the short grass plains turn briefly green after the rains. The mothers gather there in February to give birth, almost all at once, 500,000 calves arriving in a few short weeks. Then, as the dry season approaches, the grass fades, and the herd lifts its head and begins to walk north. What guides them is the question. One leading idea is that wildebeest can smell rain from far away. Storms release a soft, earthy scent when raindrops hit dry soil, a smell humans know too. That scent travels on the wind, sometimes for great distances. Researchers have watched herds change direction within hours of a faraway storm, turning toward clouds they could not possibly see. The nose, it seems, may reach further than the eye. Yet smell alone cannot explain everything. Wildebeest also seem to respond to the low rumble of distant thunder, which travels through the ground as much as through the air. Elephants are known to feel such vibrations through their feet. Wildebeest may do something similar, though the evidence is still thin and the question stays open. A second theory is simpler. The herd may remember. Older animals lead, and the route is so old that it may be carried in living memory, passed from mother to calf across many generations. A young wildebeest walking north for the first time is walking inside a crowd that has done this before. The path is learned by being inside it. Both ideas may be true at once. Memory may set the general shape of the loop, while smell and sound shape the small daily choices of where to turn. What is changing now is the loop itself. The earth is always moving, and the patterns animals trust are slowly shifting beneath their hooves. Rainfall across East Africa has become harder to predict in recent decades. The wet seasons sometimes arrive late. The dry seasons sometimes stretch longer. New fences, new roads, and new farms cut across old paths. In some places, the herd now meets a barrier where there was once only open grass. The wildebeest adjust, but the cost of adjustment is not yet fully understood. Across deeper time, these patterns have always been changing. The Great Migration as we see it today is only the latest version of something much older. During the Ice Ages, when the climate of Africa swung between wet and dry, the grasslands themselves shifted, expanding and shrinking like a slow tide. The animals walked with them. Lakes that are now dry once held water. Forests that are now grass once held trees. The migration routes we map today are the surface of a much older, slower drift, written and rewritten across hundreds of thousands of years. The same is true elsewhere. The Caribou trails of the far north, the Monarch corridors across North America, the long ocean roads of the gray whale. All of them are younger than they look. Each one is a recent line drawn on a map that keeps redrawing itself. The animals follow cues that were tuned to a climate that no longer exactly exists. How they adjust, how quickly, and what they may quietly lose along the way are open questions still being studied. For tonight, picture the herd at dusk. The sun is low and orange. The dust rises in soft clouds around their legs. Somewhere far ahead, beyond the horizon, a thin curtain of rain is falling on dry ground. The smell of it has begun to travel on the evening wind. A single wildebeest lifts its head, then another, and slowly, without any visible signal, the long gray river begins to turn. We do not fully know what they sense. We only know they sense it. And the loop continues as it has for as long as anyone can remember. Light in the sea is not the same as light in the air. It bends and softens and fades. Red disappears first in the upper few meters, then orange, then yellow. By the time sunlight has traveled 100 meters down, only a deep blue remains. Below 300 meters, even that gentle blue blue is gone. The ocean becomes a place of long, slow darkness, broken only by the small living lights of the creatures who live there. And yet, through this layered world of fading color, animals find their way. Some swim near the surface, where the sun still paints the water in shifting bands. Others travel in the dim middle layers, where light is only a memory. Some cross the deepest dark of all. Each of them seems to follow a path. We cannot see these paths, but the animals seem to know they are there. One idea is that light itself draws the lines, the angle of the sun, the way it scatters through water, the slow turning of polarized light across the sky. All of these may give a traveling animal a kind of compass. Researchers have shown that some fish can sense the polarization of light, the hidden pattern in how light waves are aligned. To our eyes, a patch of bright sea looks the same in every direction. To a salmon, or perhaps to a tuna, it may carry a faint signature, pointing one way and not another. Whether this signature alone is enough to guide a long ocean crossing, no one is sure. A competing theory says the light is only part of the story. Animals may use light near the surface, then switch to other cues as they descend. A bluefin tuna, for example, dives to great depths and rises again many times a day. In the bright upper water, it may read the sun. In the cold dark below, it may listen to the deep hum of distant currents, or feel the slow pulse of Earth's magnetic field through its body. The same animal may be running 2 or 3 navigation systems at once, blending them like a quiet song. We do not yet know how it weighs one cue against another. Then there are the lanterns of the deep. In the middle layers of the ocean, countless creatures make their own light. Tiny shrimp glow faint blue. Lanternfish carry rows of soft beads along their bellies. Jellyfish trail green and violet ribbons through the dark. Together they form what some call a living constellation, scattered through water that should be black. Some researchers wonder whether migrating animals use these patterns as a kind of map. A hunting squid may know the shape of a familiar glow at a certain depth. A young sea turtle drifting far from any shore may swim through a soft cloud of blue sparks and read something in their density, their rhythm, the way they move when disturbed. Others are more cautious. The deep light made by living creatures changes from night to night. Plankton bloom and fade. Currents push the lanterns into new shapes. A map that shifts every evening is a strange map to follow. Perhaps the glow is more like weather than like roadway, useful for the moment, but not for the year. The question of how much these living lights help with long migration remains open. There is also the curious matter of the daily climb. Every evening, in oceans all over the world, vast layers of small creatures rise from the deep toward the surface. They feed in the dim light of the upper water through the night, then sink again before dawn. This is the greatest movement of life on Earth, and it happens twice every day in silence, beneath the waves. The trigger seems to be light itself, a certain dimness, a certain color of blue, signals that it is safe to rise. But the exact mechanism and how each tiny animal knows when to turn back is still being worked out. Larger migrators travel along this rising and falling tide. Whales, sharks, swordfish all follow the daily pulse of small life. Their long ocean journeys may be stitched together from thousands of these short vertical hops, each one guided by the changing color of the water above them. The grand path across an ocean basin may simply be the sum of many small choices made in fading and returning light. So beneath the waves, there are highways. We can sense their shape only faintly from tags and tracks and patient years of watching. The animals seem to read them in colors we cannot see, in glows we cannot feel, in patterns of light that vanish the moment we try to hold them still. For tonight, the highways stay quiet and the question stays open. High above the sleeping fields, on warm summer nights, the air is full of voices we cannot hear. They are not the voices of birds or the soft hum of insects, but something stranger. They are the calls of bats, pitched far above the range of human ears, threading through the dark like fine silver wire. And many of these bats are not simply hunting. Some of them are traveling, following long invisible paths across countries and continents. Guided by sounds we are only beginning to understand. Bats are among the most mysterious migrators on Earth. Some speak species stay close to home all year, tucked into caves and hollow trees. Others move hundreds, even thousands of miles, slipping through the night sky in waves. The little hoary bat, soft brown and frosted at the tips of its fur, may travel from Canada all the way to Mexico. Other small bats cross deserts, mountains, and broad stretches of sea. And almost all of this happens in darkness, where no one can easily watch. The strange thing is how they seem to know where to go. A bat is a small, warm body, no heavier than a handful of coins, flying through air that moves and shifts and twists. Yet somehow it finds its way. Researchers have long wondered how. One idea is that bats use the same magnetic sense that helps birds and turtles steer across the world. Some experiments suggest that bats can feel the pull of the Earth's magnetic field and use it to set a course at sunset. But the details remain blurry. We do not yet know exactly where that sense lives inside their tiny bodies, or how finely tuned it really is. Another theory points to the sky itself. Bats may read the glow of the setting sun, watching the colors of dusk to orient themselves before full night arrives. They may also follow long ribbons of moving air. Warm wind rises off ridgelines. Cool air sinks into valleys. Storm fronts push great walls of moving sky from one region to another. Some researchers wonder if bats ride these rivers of air the way swimmers ride a current, letting the wind carry them while they sleep on the wing in short, gentle bursts. Whether bats truly do this, or only seem to, is still being studied. And then there is sound. A bat's whole world is made of sound. It calls out into the darkness, and the echoes come back painting a picture of leaves, branches, insects, walls of stone. This is called echolocation, the use of returning sound to map the world. In a quiet forest, a bat can build a kind of moving image of every twig in front of it, all without seeing a thing. But echolocation is mostly a close-range sense. It tells the bat about the next few seconds of flight, not about the next 1,000 miles. So how does sound help a migrating bat over a long journey? One soft idea is that bats may listen to the world around them in ways we have not yet measured. They may hear the distant rush of a river far below, the whisper of waves on a coastline, the low rumble of wind against a mountain ridge. These long, low sounds travel further than the bat's own high calls. Some researchers wonder if migrating bats use such background sounds as landmarks, the way a traveler might recognize the shape of a familiar hill. Others are not yet convinced and say the evidence is thin. There is also the question of how bats traveling together communicate. On certain nights, thousands of bats stream from a single cave mouth, rising into the dusk like dark smoke. They call constantly, each voice high and sharp, each ear listening. In that storm of sound, somehow, they do not collide. Somehow, they stay loosely together. Whether they share information about routes, or weather, or food, we honestly do not know. Some scientists suspect a kind of group knowledge passes through the colony. Others believe each bat is simply solving the puzzle on its own. What we are left with then is a picture of small winged creatures threading the night sky, listening to a world we cannot hear, following currents of air we can only partly map. They cross borders without papers. They cross deserts without water. They cross seas without rest, guided by some quiet mix of magnetism, memory, starlight, and sound. Somewhere out there tonight, a bat is flying south along a river of warm air, calling softly into the dark. It hears the land below in ways we cannot. And whatever map it carries inside its small, careful body remains, for now, mostly a mystery. On a warm island night in the western Indian Ocean, on a single beach on Christmas Island, the red crabs begin to move. Tens of millions of them, each no larger than a clenched fist, rise from the dim forest floor and flow toward the sea. They cross roads. They cross gardens. They climb low walls. The ground itself seems to ripple and shift in a slow red tide. And the timing of this great walk is not random. It is set by numbers older than any clock the crabs could ever know. The crabs arrive at the shore on a precise night, near the last quarter of the moon, just as the high tide reaches its softest, most even pulse. The females release their eggs into the surf in the gray hour before dawn. Miss the right night, and the eggs are lost. The crabs do not seem to miscount. Year after year, generation after generation, they keep pace with a rhythm written in the sky. That rhythm is the moon. The moon circles the earth once every 29 and a half days. Give or take a few hours. Its pull stretches the seas into two soft bulges of water, and the planet turns beneath them, giving us two high tides and two low tides each day. When the sun and moon line up, at the new moon and the full moon, the tides swell larger. When they pull at right angles near the quarter moons, the tides grow gentle and even. These calmer tides are called neap tides, and it is on these calmer tides that the crabs release their eggs. The math behind all of this is in its bones, very simple. The moon's orbit can be predicted to the second, centuries into the future. The tide tables for any harbor on Earth are written years ahead. We can say with confidence when the water will rise on a beach on the far side of the world in the year 2090. And somehow the crab, with a brain smaller than a pea, keeps a copy of that table inside itself. How they do this is still an open question. One idea is that the crab's sense changes in light. The moon's brightness rises and falls in a steady cycle, and small bodies may track that glow even through forest leaves. Another idea is that they feel the faint shift in air pressure that comes with the lunar pull. A third idea is that the rhythm lives inside them as a true internal clock, a kind of biological calendar tuned across long ages of natural selection. Most researchers suspect the truth is a quiet blend of all three. The exact recipe remains unknown. This kind of timing shows up across the living world in patterns that feel almost mathematical. Horseshoe crabs gather on Atlantic beaches on the highest spring tides of May and June. Their dark shells forming slow, overlapping curves in the sand. Coral colonies on the Great Barrier Reef release their eggs in a single synchronized spawning a few nights after the full moon in late spring. The water filling with soft pink clouds. Grunion fish ride the high tides onto California sand to lay their eggs in the exact window when the next tide will not wash them away. Each of these creatures lives by ratios. The ratio of 1 lunar month to the solar year, the ratio of tide to temperature, the ratio of day length to season. Inside them, somewhere, these ratios become decisions. Now, not yet. Now, the numbers extend further still. The Arctic tern follows the sun from pole to pole and covers, over a long lifetime, a distance close to 3 round trips to the moon. The bar-tailed godwit flies more than 11,000 kilometers across the open Pacific without stopping, burning its own muscle for fuel in the final days. The monarch butterfly weighs less than a paperclip, and yet travels a route measured in thousands of kilometers, drawn by a clock and a compass we have only partly mapped. None of these animals carry instruments. They do not measure. They do not calculate in any way we would recognize. And yet the answers they arrive at match the math of orbits and tides and seasons with quiet, repeatable precision. There is a kind of beauty in that. The universe runs on a small handful of simple rules. Gravity pulls, light bends, the moon swings, the earth tilts, and life somehow learns to read these rules from the inside, without paper, without numbers, without words. The red crab walks down to the sea on exactly the right night. The reef releases its eggs in exactly the right hour. And we, standing on the shore, are left to wonder how the counting is done. Return now gently to the eel. We began with this strange and quiet creature, and now we come back to it, carrying everything the night has given us. The eel has been swimming through human stories for thousands of years, and yet, in our own lifetime, something has begun to shift in its long and silent journey. For most of recorded history, eels were simply there. They filled the rivers and ponds of Europe in such numbers that they seemed endless. Children scooped young eels from streams in spring. Markets sold them by the barrel. The arrival of the glass eels each year felt as steady as the turning of the seasons. No one imagined that this slow, patient flow could ever thin. Then, sometime in the last 50 years, the numbers began to fall. The count of young eels arriving on European coasts dropped sharply. By some measurements, the inflow today is only a small fraction of what it was a few decades ago. The eels are still coming, but far fewer of them, and no one fully understands why. This is where the fragile nature of migration begins to show itself. The eel's journey depends on a long chain of small things, each one holding the next in place. The adult must find the right month to leave the river. It must reach the sea in good condition. It must cross thousands of kilometers of open ocean. It must spawn in the right patch of water, at the right depth, at the right temperature. The eggs must drift on the right current. The larvae must find food along the way. And then, years later, the young must locate the same hidden gates back into freshwater. Change any single link in that chain, and the whole pattern may quietly bend. Some researchers wonder if the trouble lies in the rivers. Dams and weirs now block many of the old waterways. An eel that once swam upstream for hundreds of kilometers may now find a wall of concrete waiting for it. Others point to pollution, which can build up in the long-lived bodies of adult eels and may weaken them during their final journey across the sea. Still, others wonder about parasites carried in from distant waters, or about the warming of rivers, or about overfishing of the young. And then there is the ocean itself. The currents that carry the tiny larvae back to Europe are slow and broad, shaped by winds and by the temperature of the surface waters. If those currents shift, even slightly, the drift can change. Some scientists think a warming North Atlantic may be nudging the great gyres into new patterns. The larvae might be carried to places that do not match their old map, or they might simply run out of food on a longer drift. No one knows which of these is the deepest cause. Most likely, it is many of them at once, tangled together. And this is what makes the question so hard. The eel does not perform its mystery in front of us. Its life unfolds in deep water, across long years, far from any place we can watch. By the time we notice a missing generation, it has already been missing for a long time. Think for a moment about how finely tuned this all is. A creature is born in a patch of warm sea no human has ever filmed. It drifts on a current that takes years to deliver it home. It changes its body 4 times. It finds a river it has never seen. It lives for decades in still, dark water. Then, on a single autumn night, it turns silver and slips away to die in the place where it was born. The arrangement is balanced on conditions no one fully controls and no one fully understands. Other migrations sit on similar quiet ledges. The monarch needs a particular grove of trees in a particular range of mountains. The salmon needs a stream that still smells like itself. The Arctic tern needs sea ice and open water in the right rhythm at both ends of the world. Each route is a slow agreement between an animal and a planet, and each agreement can be edited without warning by changes neither side asked for. The eel reminds us that we are watching something delicate, something built by deep time and held together by signals we cannot yet read. Whether the lost generations will return in numbers, or whether the long drift will keep thinning, no one can say. The question is honest and open. The answer, if it comes, will come slowly, in the patient way that all eel news arrives, quietly from the dark water, long after the fact. There is a quiet pattern that biologists keep noticing across the world. A migration that once filled a river, a sky, a coastline slowly grows thinner. The animals still come. They still move along the old paths, but the numbers fall year by year, and no one can say with certainty why. The European eel is one such story. Glass eel arrivals at the rivers of Europe have dropped by more than 90% since the 1980s. Scientists have proposed many possible reasons. Dams block the rivers. Pollution weakens the young. Parasites brought from other waters lodge in their swim bladders. Ocean currents in the Atlantic may have shifted, carrying fewer larvae toward the coast. Each of these ideas has evidence behind it. None of them, on its own, explains the full collapse. The truth seems to be a tangle, and untangling it is slow work. Salmon tell a similar story in many rivers of the northern world. Some runs that once turned streams silver with bodies now bring only a handful of fish. Warming water, lost spawning gravel, hatchery genetics, and changes far out at sea all play a part. Researchers can measure each piece. They cannot yet weigh them against each other with confidence. A river that loses its salmon also loses the nutrients those bodies carried inland. Bears, eagles, and even the trees on the banks feel the absence. The The migration is not just a movement of animals. It is a movement of food, of minerals, of life itself. Monarch butterflies in North America have followed a slow downward curve as well. The overwintering colonies in the mountains of central Mexico are measured each year by the area of forest they cover. Some winters, the colonies shrink to a fraction of their old size. The causes are debated. Loss of milkweed across the breeding range is one leading idea. Pesticides, severe weather, and changes in the forests where they rest are others. Researchers still argue about which factor matters most, and the answer may shift from year to year. Songbird migrations carry their own quiet losses. Across continents, the small voices that once filled spring forests have grown fainter. Light pollution disorients night flyers. Tall glass buildings stand in the middle of old flyways. Insects, which many of these birds depend on, have declined in many regions. A bird that crosses thousands of miles needs every link in the chain to hold. When one link weakens, the journey becomes harder, and some birds simply do not return. What makes these mysteries so hard is the sheer scale of a migration. An animal might be born in one country, feed in a second, rest in a third, and breed in a fourth. A problem in any one of those places can shape its fate. To study the full path, researchers must work across borders, across oceans, across languages. They share tracking data, genetic samples, and counts taken on cold mornings at remote stations. The picture they build is patient and incomplete. There is also the question of what the animals themselves are learning or failing to learn. Some migrations are taught, passed from older to younger across generations. When the older animals are lost, the root can fade with them. Whooping cranes, for example, once needed human pilots in small aircraft to teach a new generation an old flyway. Other migrations seem to live in the genes, written into the body before the animal hatches. If the world changes faster than those instructions can update, the path may lead to the wrong place at the wrong time. And yet, within all this uncertainty, there are also recoveries. Humpback whales, hunted to the edge of vanishing, now sing again in many oceans. Some salmon rivers, freed from old dams, have welcomed back fish that no one expected to see. Sea turtles protected on a single beach can return in greater numbers decades later. The patterns are not only of loss, they are of fragile, slow returns when the right conditions are given time to hold. Still, the deepest question lingers. How much of a migration is the animal, and how much is the world around it? A bird with a perfect inner compass cannot fly through a sky with no insects to eat. An eel with an ancient map cannot reach a river it can no longer enter. The navigation, however it works, depends on a living planet to navigate across. When one fades, the other falters. So the mystery here is not only how animals find their way, it is whether the ways themselves will remain. That part of the question we cannot yet answer. We can only keep watching and counting and wondering. The routes the animals follow are old, older than most things on Earth that we still call ancient. The Salmon stream may have been carved by a glacier that finished melting only 12,000 years ago. But the deeper pattern, the urge to return to fresh water and lay eggs in cold gravel, is far older than that single stream. The eels drift across the Atlantic may have begun when the Atlantic was a narrower sea. The Monarch's tilted flight toward a Mexican mountain may have started before that mountain or its current shape. This is one of the quieter wonders of migration. The map the animals carry is not the same map the Earth is drawing today. The Earth keeps moving. The continents keep drifting on their slow rafts of stone. Rivers cut new channels. Coastlines flood and retreat. Forests creep north as the climate warms, and grasslands push south when ice returns. The animals must adjust their old routes to a planet that will not hold still. Think of 100,000 years from now. The shorelines you know will be gone. Some islands will have sunk. Others will have risen. The Great Lakes may be reshaped or drained. The rivers the salmon climb may flow in different beds. The currents in the Atlantic that carry baby eels home may shift, weaken, or split. We have already seen small versions of these changes within human memory. The Gulf Stream wavers. The jet stream wobbles. Sea ice that birds once rested on has thinned and broken apart. 1,000,000 years from now, the picture grows stranger still. Africa will press harder into Europe, closing parts of the Mediterranean. Australia will drift north toward Asia. New mountain ranges will lift slowly into the sky. The Sargasso Sea, the calm patch where eels seem to gather, sits inside a great spiral of currents held in place by the shape of the Atlantic basin. If that basin changes shape, the spiral will change too. We do not yet know whether the eels can rewrite their ancient route to match. Some researchers wonder if migration patterns are flexible, edited gently across many generations. Others suspect that some species are locked into roots so old that they cannot bend fast enough. Push the clock further into hundreds of millions of years, and the continents are predicted to gather again into a single great landmass. Geologists have given this future supercontinent several possible names and shapes, because we cannot yet know exactly how it will form. The oceans will pool around it. The interior will be vast and dry. Many of the migrations we know today, the pole-to-pole flight of the tern, the long swim of the gray whale along a familiar coast, will simply have no coastline to follow. New migrations will take shape. New animals, perhaps descendants of the ones we watch now, will find new corridors of food and weather and safety. And then, in roughly 1 billion years, the sun itself will grow warmer and brighter. The oceans will begin to thin into vapor. The atmosphere will change. Life on Earth, if it still flourishes, will look very different from the life that lays eggs in our rivers tonight. The instinct to move with the seasons, to seek breeding grounds, to follow a memory written in cells, may persist in some form long after the species we love have faded, or it may not. We do not know how migration ends, only that the planet beneath it never stops moving. Yet something hopeful sits inside this long view. New things keep forming. New rivers, new reefs, new forests, new flyways. The earth that erases an old route is the same earth that draws a new one. Birds we have not yet named may one day cross seas that have not yet opened. The wandering urge is older than any single map. It seems to belong to life itself, not to any one landscape. For tonight, the question is gentler. How much of the current pattern can survive the changes already underway? The warming we can measure now is faster than most of the slow shifts of deep time. Animals that took 10,000 years to learn a route may have only a few human lifetimes to learn a new one. Some will manage, some we fear will not. Which ones and why? And whether their cousins can carry the knowledge forward remain open questions that no one alive can answer yet. The eel keeps drifting. The tern keeps flying. The salmon keeps climbing. They carry an old map across a young, restless world. Somewhere ahead, the map and the world will meet a different shape, and the animals will quietly redraw the line between them. Step back with me now, away from the eel and the salmon, away from the tern and the whale, and look at the whole quiet picture from a great distance. A small planet turns slowly in the dark. Its surface is mostly water, with thin skins of land between the oceans. And across that surface, every hour of every day, millions of creatures are moving, not wandering, moving with purpose toward places they have never seen, along paths older than any human road. There is something humbling in that picture. We have built tools that can measure the faintest tremor in a distant rock. We have mapped the genome of the smallest fish. We have sent thin metal probes to the bottom of the deepest trench. And still, when a young songbird the weight of a coin lifts off in autumn and finds its way to a forest it has never visited, we cannot fully explain how. Some part of the answer lives in the atoms themselves. The iron in a salmon's body, the calcium in a sea turtle's shell, the carbon in the wing of a monarch. All of it was made long ago, deep inside stars that lived and died before our sun was born. When those stars collapsed, they scattered their elements into clouds of dust. Our planet formed from that dust, and every cell of every migrating animal carries that ancient material forward, still moving, still finding its way. Seen from far enough away, a migration is just matter flowing. Iron flowing through the ocean inside the blood of a tuna. Calcium flowing across the sky inside the bones of a goose. Salt and water and protein drawn along invisible lines by signals we are only beginning to read. The animals do not know any of this. They They simply feel the pull and follow it. And somehow, that feeling is enough. One of the strangest possibilities raised by modern research is that some animals may sense the world through the rules of quantum physics. Those very small, very odd rules that govern how particles behave. The idea is that certain proteins in a bird's eye may respond to Earth's magnetic field through pairs of linked particles. If that is true, then a robin crossing the night sky may, in some quiet way, be reading the magnetic field through the same physics that shapes the inside of a star. That is one theory. Other researchers think the answer will turn out to be simpler, hidden in ordinary chemistry we have not yet mapped. The question is still open. Either way, the picture is the same. The migrating animal is not separate from the planet it crosses. It is woven into it. The bird and the magnetic field are part of one system. The whale and the ocean currents are part of one system. The eel and the slow turning of the Atlantic are part of one system. Pull on any thread, and the others move. We sometimes think of ourselves as the watchers, standing outside, taking notes. But we are inside the system too. The same iron that points a robin north sits in our own blood. The same water that carries a young eel across the ocean fills our own cells. The same light that wakes a monarch in a Mexican forest reaches our own eyes. We are not visitors here. We are part of the flow. Perhaps that is what the animals seem to know that we do not. Not facts, not maps, not theories. Something quieter. A sense of belonging to the planet so complete that no instructions are needed. The tern does not wonder whether the pole is real. The salmon does not doubt the stream. The eel does not hesitate at the edge of the deep. They simply go, because going is part of what they are. And we, who ask so many questions, may be slowly learning to feel a small version of the same thing. When you stand on a shore at dusk and watch birds moving south in a long, uneven line, something in you understands without words. When you hear a story about whales calling across an entire ocean, something settles in your chest. The body knows it is part of a larger pattern, even when the mind cannot quite explain how. The animals will keep moving tonight while you sleep. The eels will drift in their dark current. The terns will glide above cold water, the turtles will follow a memory written in salt, and the planet will turn as it always has, carrying all of us together through the quiet dark, made of old starlight, finding our way by signs we are still learning to name. So we come to the quiet edge of the night. The questions have been laid out, one after another, like soft stones along a path. The eel still vanishes into the warm blue water of the Sargasso, and no one has ever seen it spawn. The tern still flies from one end of the world to the other, guided by something we have not yet named. The salmon still finds the small stream where it was born. The turtle still finds the beach. The butterfly still finds the mountain. And we still stand at the edge of all of this, watching, wondering, not quite knowing. That is all right. The not knowing is part of why the world is beautiful. Picture the earth tonight as it really is in this moment. A great blue sphere turning slowly in the dark, half of it lit by soft sun, half of it resting in night. On the dark side, lights from sleeping cities glow like scattered embers. Beyond them, the oceans roll on, silver and black, lifting and falling in their slow, steady breath. Somewhere out there, a whale is singing into water no human ear will ever hear. Somewhere, a small bird is sleeping in the air, one half of its brain awake, the other half dreaming. The moon is rising over a quiet shore. The tide is coming in, drawing tiny crabs out of their burrows in a soft march no calendar taught them. A forest on the other side of the planet is full of fireflies pulsing in the dark. A mountain holds 1,000,000 butterflies sleeping in folded clusters on the bark of fir trees, their wings closed, their bodies still, waiting for a sun they trust will come. In the cold north, a herd of caribou is bedded down on the open tundra. Their breath rises in small clouds. The stars wheel above them, the green ribbons of the aurora moving slowly across the sky. Tomorrow they will walk again along the same long path their grandmothers walked. And no one knows exactly what map they carry inside them. In the warm south, a sea turtle is gliding through dark water, her flippers moving in a slow, steady rhythm. She is on her way back to a beach she has not seen in many years. Something inside her remembers it. We do not know what that something is. is. We only know that it works, and has worked, for longer than there have been humans to wonder about it. The earth holds all of this at once. Every migration, every quiet journey, every animal moving through the dark, by a sense we cannot share. The planet does not need us to understand it in order to keep turning. The eels do not need our maps. The whales do not need our charts. They have their own ways, older than our questions, deeper than our instruments. There is comfort in that. We are small here, and the world is large, and the world is doing well. Somewhere, right now, a salmon is tasting its home river for the first time in years and turning toward it. Somewhere, a tern is gliding above a southern sea, halfway through the longest journey on Earth. Somewhere, a young eel the size of a leaf is drifting in a slow blue current. On its way to a coast it has never seen and will somehow recognize. You can let your shoulders soften now. You can let your breath slow. The mystery does not need to be solved tonight. It has waited patiently for centuries, and it will still be here in the morning, gentle and unhurried, ready to be wondered about another evening. Maybe in your lifetime, someone will find the answers. Maybe a research ship will record an eel spawning in the dark Sargasso water at last. Maybe a new instrument will reveal the magnetic compass hidden in a songbird's eye. Maybe a child being born tonight will grow up to map the secret highways of the ocean, and we will finally see what the animals have always seen. Or maybe these mysteries will stay mysteries for a long while longer, quiet gifts the earth keeps for itself. Either way, the world will keep moving. The currents will keep flowing. The seasons will keep turning. And somewhere out in the great soft dark, an animal will be on its way home, guided by something we cannot quite name, arriving exactly where it is meant to be. Rest now. The earth is spinning gently. The oceans are calm. The migrations continue without us, faithful and ancient. You are held by a planet that has been taking care of its travelers for a very long time. And tonight, it is taking care of you too. Subscribe for a brand new Earth topic every night. One tap, and something wonderful is waiting for you tomorrow. Sweet dreams.